Why don't we feel the Earth spin? The Earth is spinning at over 1,600 kilometers per hour at the equator. That's faster than a commercial jet. Yet, as you're watching this, you probably don't feel a thing. Why is that? How can something so massive, moving so fast, feel like it's standing still beneath our feet? This question has puzzled humanity for centuries. Today, we're diving into the science behind our planet's dizzying spin. By the end of this video, you'll not only understand the answer, but also see your everyday world in a whole new way. The mystery of motion. Let's start by thinking about motion. Have you ever been on a plane cruising at high altitude? Once the plane reaches a steady speed, you barely notice the movement, right? You can stand, walk around, and even pour a drink without spilling. This phenomenon is similar to what's happening on Earth. But to understand why, we need to break this down further. The first concept we need to explore is relative motion. Everything on Earth, including you, me, the atmosphere, and the oceans, is moving with the planet. If the Earth is spinning at 1,600 kilometers per hour, so are you. And because we're all moving together, there's no noticeable change in motion to alert our senses. Imagine you're sitting in a car, moving at a constant speed on a smooth highway. You don't feel the motion until the car speeds up, slows down, or turns. Inertia and sensory perception. This brings us to another key concept, inertia. You might remember this term from physics class. Inertia is the tendency of objects to resist changes in their state of motion. It's part of Newton's first law of motion. Since you're already spinning with the Earth, your body doesn't feel any change that would make you aware of the rotation. But there's more to it. Our sense of motion relies heavily on acceleration. When you speed up, slow down, or change direction, your body senses it. That's because these changes create forces, which your body detects. But Earth's rotation is constant and steady. There's no acceleration or deceleration. So there's nothing for your inner ear, the part of your body that helps sense motion, to detect. The science of spin. The Earth spins around its axis once every 24 hours. At the equator, this means a speed of about 465 meters per second. But near the poles, this speed is much slower. Why? Because of the shape of the Earth. Our planet isn't a perfect sphere. It's an oblate spheroid, meaning it's slightly flattened at the poles and bulging at the equator. This shape causes the rotational speed to vary depending on where you are. But no matter where you are, the rotation remains constant and smooth. That consistency is crucial. Imagine you're in a car that's moving at a steady speed on a straight road. You don't feel the motion unless the car accelerates, brakes, or turns. Subtle clues of Earth's motion. Here's a fascinating twist. We actually can feel the Earth's rotation indirectly. Have you ever watched the stars at night and noticed they seem to move across the sky? That's not the stars moving. It's us spinning with the planet. The apparent movement of celestial objects is one of the few ways we experience Earth's rotation visually. Another indirect effect is the Coriolis force. This invisible force affects the direction of winds and ocean currents. It's why hurricanes spin in opposite directions in the northern and southern hemispheres. The Coriolis effect is a subtle reminder that the Earth is, in fact, rotating. Gravity versus centrifugal force. If the Earth is spinning so fast, why don't we get flung off into space? The answer lies in gravity. Gravity is the force that pulls objects toward the center of the Earth. It's incredibly strong, far outweighing the centrifugal force caused by the planet's rotation. At the equator, the centrifugal force slightly reduces the effect of gravity, but it's not enough to overcome it. This balance keeps us firmly grounded. To put it in perspective, The centrifugal force at the equator reduces your weight by only about 0.3%. So, if you weigh 70 kilograms, that's a reduction of just 200 grams. Hardly noticeable, right? What if the Earth stopped spinning? Now, you might wonder, what if the Earth suddenly stopped spinning? That's a thought experiment that truly reveals the power of our planet's motion. If the Earth were to stop abruptly, everything not anchored to the ground would continue moving at 1,600 kilometers per hour. Buildings would collapse. Oceans would surge, creating massive tsunamis. And the atmosphere would become a wall of wind, sweeping across the globe. It's a chilling reminder of just how much energy is tied up in Earth's rotation. Thankfully, such a scenario is purely hypothetical. The forces keeping our planet spinning are immense, and they've been in place for billions of years. The gradual slowdown. But there's one more question to consider. What if the Earth's rotation gradually slowed down? This is actually happening, although very slowly. Tidal forces between the Earth and the Moon are causing our planet's rotation to slow by about 1.8 milliseconds per century. Over millions of years, this could lead to longer days. But for now, it's nothing we need to worry about. In fact, the slowing rotation has a surprising benefit. It's responsible for the Moon gradually moving farther away from Earth. And this delicate dance between Earth and Moon has played a crucial role in stabilizing our planet's climate over time. A new perspective. So let's circle back to where we began. Why don't we feel the Earth's rotation? The answer is a mix of physics and perception. Relative motion, inertia, and the lack of acceleration all play a role. We're part of a system that's moving together in perfect harmony. It's a testament to the incredible stability of our planet, and it's a reminder of how much we take for granted in our everyday lives. Next time you step outside and look at the sky, remember this: you're standing on a spinning sphere, hurtling through space. And thanks to the wonders of physics, you don't even feel it. But now you understand why.